Welcome back, people. There are a lot of updates. I did not stream yesterday, so let's go. So the first thing that I did was let's just open the code base. The first thing that I did was I rewrote the entire MCTS thing because what we did was incorrect. Let it just open up. The second thing is I improved the MCTS by adding Dirichlet noise in the action selection, so this way it is able to actually go over a lot more actions. Third thing is that the web app is now complete. You can actually play with it. And lastly, I improved the loss function. I realized what I was doing was incorrect, and now I fixed that. I have not tested it yet, and so what we are going to do is we're going to first verify the new loss function by training a very simple network. Let's see if it actually it actually learns something. Second is we are going to code simple normalization layers, so this way we can get a better understanding of what normalization is doing. And then I promised we'll do a denormalisation layer in another stream, but we are going to code the denormalisation layer and see if it actually improves the regression methods. And lastly, we are going to just train new networks based on this. Okay, so what was the thing that I was doing wrong? Now consider this as a very good problem. What we were doing is, our assumption was that the model is going to be predicting the action value and the what is the policy, basically. Q and P is equal to M times states, and each state can then be interpreted as a set of moves that goes from say M0 to all the way to M of N. Now this is wrong because the Q value is actually Q of state and action. What that means is, in this given state, if I take a particular action, what is that action going to reward me with? So the way you define it is as follows. You say that again we are going to go over our backup diagrams. It's much more easier that way. So here the QSA is actually the this particular line. What that means is, given this state and given taking this action, what is the value that I'm getting from taking these two things? Now QSA actually is sum of all the so this thing is going to be just deterministic. So it's basically the sum of, or mean of, you can say, of all the values that you're getting from the following states. What that means is, if I take this in this state S, I take this action A and I reach state S prime 1, S prime 2, then Q of SA is basically the amount of reward that I get and what is the value of these two states. Now this is different from the value of the state, which is V of SA. What we did incorrect was, our assumption was that the model is actually returning this thing, but in fact the problem came when you actually during coding you had to update the Q values of the network. So when you updated when you were in the node and you just updated the Q value, the value, then it would actually it won't run because it won't be able to update it properly. So you're trying to define two different things as the same object. Now I have updated that. So now each node, basically the model, now what it does is, this thing actually is V, which is basically V of S. So this thing is now the actual value of that particular state. So what I now do is, considering state Mn, or what you can say is state of 0, which is the root node, you take all the legal actions from the state, then you run a policy network, and each policy network is now going to give you what is the value of state s of s plus 1 comma the policy of taking each action, which is basically policy at state s plus 1, which means what are all the possible actions, what is the probable priors of all the actions that I can state that will happen in state of s plus 1. So I updated the code, and now the entire MCTS is basically one big function. Let me just make this thing larger. Yeah. So you give it the expand, you give it the model, you give it the root node. What is the board, depth, vocab, inverse vocab, nodes taken, which is the update list. So the first thing is, for this root node, I need to determine what are the probability of the next moves. In this case, all the next moves are basically going to be all your possible legal moves. What that means is, first I determine for this particular state what is the value that I'm getting at this root node. So values is values kp1 is what is the value that I'm getting at this state. Then for step 2 is expansion, which is for all the next moves, what are the possible probabilities of the next board state. So you do a k plus 2, which is you batch all the possible legal moves, join them together, and now what we do is, now for this root node we have k plus 2 depth possible tree, so we add this to root node children. The priors for this thing are k plus 1, so logic blah 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 blah. You define the node. Another thing we do now is we check if the root node has if root node already has visited this particular child. So this way, if you remember, we were getting children like 200 300 children, which is not possible on a chessboard, but now this fixes it. What we do is we simply update if this particular root node has already been visited earlier and is stored in root node children, then you simply update the priors to the current priors. Else we actually add this thing to the root node. Third is the selection, which is first we get all the action values. For this we get the get action value with exploration. Another thing that I've changed is I don't use the adjusted action value now. I simply use what was given in the paper, which is CPUCT. CPUCT. Let me just open it. Yeah. The code, man. All the actions are taken based on so this is what we are trying to do. So this is all your actions, and the action is finally determined by here. So CPUCT times what is the prior of taking this thing, which is basically the policy network's output times this thing, and so we have coded that up. np.sqrt, what are all the possible states on this particular board, divided by what is the number of times that this thing has been visited. Now we also initialize with n is equal to 0 because this is how it was defined. Next up, what we have changed here. So we get all the action values, and which is aq plus 1. Then we add the Dirichlet noise, which is Dirichlet noise basically is a probability given the some alpha value. It generates a distribution, a probability distribution. I am not exactly sure how it works, but what it gives you is something on these lines. So I can just give it a prior probability, and the sum of all these values, each row is going to be 1. We're going to come over this piece later. So now you add this thing, you merge these things based on some row value, which in paper is defined as 0.75. So 0.75 times the action value plus 0.25 times the noise. This way we can ensure that if we run a lot of simulations, then we are able to get to very good, we can actually cover a lot of these actions. Next, child node is basically we simply arc sort what is going to be the action value and choose the action with the highest state action value. Remember, now what we are doing is we are determining the state action value, and now the state action value is actually, you can see at each step we determine it in a separate way, and we don't need to store it. Then yeah, so get action value with exploration. So when we initialize it, you can see that self.action value is 0. Yeah, so self.action value is now 0. What that means is when you have come to this node for the first time, this thing is 0, which is action value is 0, self.end is 0. So the entire thing just depends on the what is the probability of this particular situation of taking this particular action. Then you take that node, add that to nodes taken list, be future, and step 4 is evaluation, which is the entire copy of what our previous thing was. Now backup, you can see now we have two different action values, which is state value and action value, and you update the action value in the n factor, and you define an MCTS, which basically runs this thing for some simulations. And post that, let's just run this thing and I'll show it to you. Did I fix this thing? I think so. Alright. So I take a board for some n number of moves. This thing has already happened, and yeah, I define what is the root node, what are the prior probabilities, and next what we do. So we need to run this code because we need to know what is the values for this board, which is when I've taken all these actions, what is the what's going to be the board value. I run an MCTS. It's going to take a minute and a half to actually run. Oh, this thing is super slow today. Let's restart this. Yeah. And my laptop's starting to make some noises. Yeah. This thing is taking a lot of time. So you know what, let's just skip it. So this way what you can see is I have updated the print MCTS function. Now it prints much better logs. And lastly, I have a select action. Now remember, the action selection does not work on the Q value thing. It actually works on based on the probabilities of the number of times each node was visited, which means that the node that was visited the maximum number of times will be visited. That's the action that is going to be taken. Okay. You know what, let's just kill this thing. I don't know, man, why is it doing this? There are a lot of issues with using WNB because you initialize it and it locks certain threads and all that shit. Alright, anyways, so you can see for this particular root node, this is what was the distribution when I ran the simulation 123 times. So most of the nodes were visited 0 times. Now this is most likely a bug. We'll fix it later, but I think if you have a network that's trained pretty well, you'll be able to mitigate this issue. And finally, the probability distribution for taking all these things comes from a certain temperature. In paper they use the temperature of 0.65, and so this is the probability distribution that you get for taking all those actions. Then all you have to do is you define what is the you sample based on this particular distribution. I've also added this to the code. Yeah, so you can now simply define what is the MCTS, search based on MCTS. What it is going to do is it's going to define the root node, tell it to run the MCTS function for all these things, define what is the move probability, which is the probability distribution of taking any of these moves, and then finally you say self.betterChoice, and it's same as sample, because in paper you know what, network error, entering reconnection low. PS, no. How do I determine kill Python process terminal? pkill-9 Python. Does it work? No, it does not. PSOX. grep general regex pattern Jupyter. Okay, Jupyter Lab, no browser. I would like to kill these processes. These are the crude Python in second. In short, you can kill this thing. Xargs kill 9. Okay. Xargs kill -9. Illegal process ID. PS args grep Jupyter. Kill -9 this thing. No, this is not the process ID. Is this the process ID? Okay. Resources. Let's go. What is that noise? What? Is anything open? Guided learning server 0. You can say Jupyter notebook. Oh, cool. Jupyter notebooks, it's an unpopular opinion, but Jupyter notebooks are better than Jupyter Lab. Jupyter Lab just has a bit of font and all that, but it's actually much worse. How to disable WNP? Yeah, that's correct. Okay, we are just going to do 100 samples. This should take a minute or minute. I know it's so much smaller. I think when we were running it, it was starting from 0. I think that might be something might have something to do with it. So now you're seeing that it's actually analyzing at least 10 to the power 4 nodes, and which is good. So yeah, we'll just let it run for a while. another thing that we're going to do today is we're going to update Python 3. What we're going to do is we're going to run new norms. No, norm practice. So we're going to start learning, start by learning what exactly is normalization methods, how normalize, what is the difference between different normalization methods, what's a layer norm, how is it different from batch norm. We're probably not going to do instance norm or group norm. We'll just continue with batch norm only. Now values of x over a mini batch b. Parameters to be learned are gamma and beta. So you define what is the mu, you define what is the variance, and you do basically a simple normalization and you do a shifting, scale and shift. Okay. Oh my god, the laptop. So I should probably keep it over something. You know what, let be. It'll calm down. It is taking 3 minutes or so after all, but it's just going to a depth of 10. Ideally the depth should be at least say 20 or 30, at least 20. This way it can look, say we can say 20 moves into the future. So one way to think about it is, if you have a very good network, then you don't need to go to a very large depths to figure out what is the exact value, because if you just take one move and it's giving you a pretty accurate value, it's giving you a value that is very close to what can actually happen, you can say that it has a very good intuition. That is how you define intuition in these models. Okay, it's being done, it's over. So now the iteration speed actually varies based on what is the board state, etc. So it has visited 18,428. What you're going to do is you're going to print the MCTS. You can see now it's giving you a beautiful log along with what was the depth till it actually searched. So you can see that the root node of 2 was, there were 2 different iterations where root node of 2 was searched. And we do an action value selection. Now you see it has visited all these nodes, and based on that it's giving me this kind of a distribution of what how I should sample it. So basically it's overwhelmingly towards what is this 55, and that's it. That's how our MCTS is now far better than what it was in the previous version. Okay, now let's study what is batch norm. Batch norm. Import numpy as np, import torch, and import matplotlib.pyplot as plt, matplotlib inline. Now I can define a certain vector which is np.random dot you can say uniform, not uniform, you're already giving it rand, and this is defined it as batch size of 2 and a sequence that has 14 elements in it. Oh, what was this? It gave me this particular value. Now I can just calculate what is the variance of this thing, which is np.mean x and np.var. Yeah, np.var x. So the mean here is 0.5 and the variance is 0.08. What this is defined what a batch norm is, what standard norm is. In standard norm terms, what you would do is you would do something like this: np.mean x divided by what was the variance of that thing. Yeah, you have the variance and you have some epsilon, which means np dot divide by np dot sqrt np dot var. Now you're already getting the variance, right? Yeah, plus you define a very small, very small epsilon, let it be 1e minus 5. Oh. Yeah, and now you can say something like this. Now the mean is very close to 0 and the variance is somewhere around 1. Right. So this is your standard what do you call, batch normalization. The reason you now you need learned parameters is so they can help you with the shifting. Now what would a denormalization look like is denormalization. What denormalization looks like is if you already have a distribution that has a size of 2,14, so 7, right? So what you can do is you can actually just say this thing. Wait. Oh, not uniform. Normal. Yeah. You have something very close to this here. Yeah. So you have something very close to this, which gives you a variance mean of somewhere around close to 0 and some variance that is close to 1. What denorm would do is we do an inverse operation of this thing, which is we actually add what is going to be the mean and we multiply it by this thing. So now the out is this, and you can see so now the mean is actually shifted and the variation is slightly changed. Okay, now there is no theory regarding it, but what Geohot was saying is that this actually works better for regression. And so let's define this thing. Yeah, let's actually just define. Let's train a small network. Simple norm, and this is denorm. And what you're going to train is we're going to train a small network. Again, we need to actually define some we need to define a very simple regression data set. In this case, what you're going to do is instead of taking the sign value, we are going to be predicting what is going to be an addition of two normal functions. Yeah, let's just do that. np.random.normal. This basically also becomes our input. Size is equal to mu lock. Okay, lock is equal to 0. Scale is equal to 0.5. Oh, and then you can just take this thing. You can write it. Yeah. Size is equal to 10 cross 3. That's it. Okay. Yeah, so variance is the square root of what is the standard deviation. So you can also say np.sqrt 0.5. Oh, am I right or wrong? What is the, I think I messed up. Standard deviation formula. Yeah, so define standard deviation using this. Oh yeah, okay. And variance is merely the square of it, which means you can just np.stdxo, and you can just multiply this. You would get this approximately the same value. Yeah, I was wrong, but you know, it's good. Now I learned something. Now let y is equal to what is going to be the target, which in this case is going to be 1, and let the scale actually be much larger, so you can see this. Yeah, so you have y and you have y. Okay, so you have y. Let's just print x and y together. So you see, this is supposed to be the input and this is supposed to be the output of this particular function. We're going to create at least 100 samples so our model can learn effectively. Okay. Now x is equal to torch dot tensor x dot float, and we're going to do with y, so you have x and y like this. Perfect. And we're going to define a simple bozo. Yeah, boz. Oh, not that. So tricky. Let's just call it Bobnet. So original, but okay. And we are going to use one layer normalization method, and another method is going to be our denormalisation method. So we'll probably also need to code that. So you have super dot init self dot lin is equal to nn dot torch dot nn dot linear input features 3, scale it up to 6, self dot ln is equal to dot layer norm, normalized shape is equal to 6, yeah, and self dot out is equal to this thing, this thing 6 to 1. Def forward is self x and out return self dot out. We probably should also add yeah, you know what, let's just define this thing as nn dot sequential. And this thing is now just going to be this, and all I have to do is self dot m x. Cool. Bob is equal to bobnet. You have Bob, you have Bob. So the number of parameters here is basically 18 plus 6, that is 24, plus 6 plus 1, which is, I think so. You know what, we'll figure it out later. And just to check, what I can do is I can just, yeah, so Bob, and Bob, our input is going to be x up to 10. Okay, perfect. So loss is equal to, sorry, ypred is equal to bob times x, and loss is equal to this minus y squared, oh my god, sorry, y squared. So we just write loss, and we also need to do loss is equal to mean of this thing, 1.96, and okay, cool. See, this becomes a loss, and we define an optim. Optim is equal to torch dot optim dot Adam, because it just, some things just are much better. Bob dot parameters lr, yeah, whatever, it's fine. What is this? And what we do is, for I in range 10, let's just run for 10 epochs. You have this loss dot backward optim dot step, and we'll just print loss. Alright, so loss is decreasing. Let's just do it for, if I do a larger learning rate, what happens? 0.1. Yay, it's not really good. Maybe. So loss surely decreases. Yeah, and now we define, we need to define what layer norm class denorm, and then dot module def init self, and we have features. Let's just look how the layer norm is defined here. Torch layer norm functional, because the problem with torch is that all this in the end just, you know, just calls a functional method only. Torch layer norm functional GitHub. Yeah. So you have a layer norm, but initially, you end of the day, you actually just send it to a functional thing. So annoying. No. But we can use this. We can use this. Okay. So first is the normalized shape. I define what is an epsilon element wise affine. I know what that is. Self dot weight is defined as this thing. Parameter dot tensor normalized shape. If I turn element affine off, let's see what happens then. You know what, let it be. We're not going to play around with this thing. Yeah, if I do an element wise thing, it learns faster. Cool. So we are going to just copy paste a lot of this code. Yeah. So this thing is nothing. I do this thing. Now wait a minute, is that a layer norm? Is nn.module? Yeah, it's a module, it's good. And normalized shape is numbers.integral. Yeah, so this basically gives you this is a normalized shape. Self.normalized shape is tuple normalized shape. Epsilon is going to be 1e minus 5. What is the default? Yeah, 1e minus 5. Element wise affine is, of course this is true. So you have this and you have this. You have this. You don't need any of this. This is true. And forward, basically just do this. Self.x. I see it's so annoying. It does all this, and at the end it's just sends it to a functional thing. It's wrapped in so many layers. PD engine, normalization, and then dot functional. Yeah, this is where you want to go. Layer norm, if not jet is torch.layer norm. Torch. PyTorch engine. No, that's not it. Helpers normalization dot py model dot net. No, you know what, we know what we have to do. We don't need to do any of this. What we can define it like is x. So first we need to define what are the moments of this thing. Does torch.mean work? X.mean, okay, and x.var. Perfect. So I have this thing which is mu is equal to x.mean and which is sigma, let's just call it var, is x.var. And denormalization actually works like this. Okay. Yeah, so you have mu and you have var and you return out. NN is not defined. Yeah, torch dot nn dot module parameter. It registers a lot of things. Have we done that correctly? Alright, cool. Now we again define a barnet. We do denorm instead of this thing, and we do this whole thing again. Let's see. Parameter is not defined. Okay. Is it a torch dot parameter? Alright, it's a torch dot parameter. Torch has no attribute parameter. Where is parameter coming from? Torch dot nn dot parameter dot parameter. So you have torch.nn.parameter. Name init is not defined. Okay, what is init? From dot dot import init. This thing? def init common ops add ops.list. It's basically just an initialization. So what we're going to do is we're going to just copy initialization from our model. The way we initialize all these things is we do this, and so we are going to define an initialization function, which is this thing. And what we're going to do is we're going to say bob dot apply init weights and then it's not defined. Okay, charge dot mn and dot embedding dot mn dot linear dot mn dot linear. Okay, so it's decreasing. And now what I do, instead of reset parameters, is self dot apply init weights. See, it's working now. Can't call numpy on tensor that requires grad. What? Okay, does this work? Oh, np dot, no, it's tarch dot sqrt. Yeah, now you're talking. Actually, there's a larger issue. So if I do 1000, it doesn't learn jack shit. No, wait. We can you plot this? B can just say losses is equal to this dot append loss dot item, and we can just do plt dot plot losses. And we'll do the same thing here. And we'll also do this. So initially the loss does decrease, but it has a more horrible loss thing. Okay, what if I just train for first 100 steps? Okay. Oh, interesting. If I do it for 300, what happens then? Oh my god, it actually works. Can't believe it. And if I do this for 300, first 400. Wow, denormalisation actually works better. Crazy, man. Oh, you know what? Let's take a quick 5-minute break. So denorm actually works. What we're going to do is we're going to apply this thing to our code, and we're going to make better architecture. We're going to code a little bit more, maybe improve the architecture things a little bit. So not exactly architecture, but the way we run code. Okay. So okay. Wow, this is actually very interesting. Even though the loss is giving me a higher loss, but much more smoother. So the minimum loss this thing got was 1.7855 something. That's still better, but the good thing is that the maximum loss is pretty low. Yeah. Well, this thing is worse. But see, what is happening is that it's continuously getting to the top maximum loss, whereas this does not happen here. What happens if I just run it for 5,000 steps? You boy! Oh, it goes berserk. Oh wait, we did not apply. No, it has already applied init weights. Where are you going? Not going to put it here. Oh, now it's going to work better. I have a feeling that this is not any good. Oh, I was wrong. Wow. You know what? It's still better because it's a lot less squiggly. Moreover, it's a random data. It's not really correlated. What if, however, what I did was like this: x is equal to np dot y is equal to np dot sum, x axis is equal to -1. What is y now? Yeah. Np dot sine of this thing. Yeah. I'm going to reshape it. Reshape -1, 1. Now we're talking. What's crazy? Why now? The work. Okay. What happens with this? Yeah. I have minimum loss is 0.003 while the maximum loss is 0.43. The minimum loss is 0.17. Is this actually better? Let's wait a minute. This thing, when initializing, is actually supposed to if layer norm or is instance. Yeah, you need to define this thing first. That was our mistake. And so this thing actually goes to the top now. What I'm going to do is, yeah, you go here, mate. Oh, what was the error? Talking about 0.02, whereas this thing goes to 0.008. Whatever it is, seeing that denormalization. So first of all, are we doing this thing even correctly? Now what we are saying is, what is denorm? Okay, let's just add this thing here. You know what? Not here. X. I'm going to do it here. Denorm. So the way a conventional normalization works is you have an input X and output Y is given as follows. Y is equal to, so right now we're just checking batch norm. What is the method for layer norm? A gamma and a beta, which is the learned functions. Am I too stupid for this shit? Probably am. But you know, who isn't? Right. Y is equal to slash frac x minus mu of x divided by SQRT. Where is it? Just divided by sigma to the power 2 minus plus epsilon. Alright. So this is how your current layer norm works. Now if you have a denormalization method, it would assume that you already have all the information normalized. So what you would do is so what this means is, now the output Y is normalized, right? Whereas in layer norm, whereas in denorm we say that X is normalized while Y is denormalized. So can you write it as follows? You can say Y, basically this thing is replace the X and Y, which is this thing. Okay. Let's see. This is something called denormalisation. Another sequel. Neural net. There is not. You know what? Let's open that particular stream. YouTube. And from YouTube we go to comma.ai archive. Comma.ai archive. Alright. In full honesty, the first idea that I had that I wanted to train something on chess came from watching this stream. But I did watch that video.
I make them, but you know, like driving the honest and all that. Biggest failure of 2020. The white panda. We're never going to bring back support. Add and multiply, right? And just.
I think this is it.
Without a high precision GPS. Well, could we write a version of it that works engineering time, right? It shouldn't. And also remember, you can, right? It's open source. If you want to invest the time to backport the new params learner or white pandas, you can. You want to get a cheap supported car for comment. It's all pretty cheap, right? It's all pretty cheap. I'm hoping that the 3D, what I've been working on, guys, you heard of batch normalization? You know what I came up with yesterday? Unbatch normalization. The layer is called denormalize, and it's literally batch normalize in reverse, and it works. You know, if I wasn't lazy, I'd write it up in a paper. But this is all the summary you get. Basically, take your running mean and your running variance, put some momentum on that, and just, instead of subtracting and dividing, add and multiply, right? Denormalize. Batch norm turns inputs into mean 0 variance 1, right, on the output. Denormalize takes 0 mean 1 variance inputs and turns them into whatever the real outputs are. So yeah, if you're a machine learning researcher and you're doing regression, check out the denormalized layer.
That guy's interesting. So it is basically what he said is, instead of doing this, we do this, and instead of frac, what we are going to do is we are going to define it like this. Okay. Wait a minute. Oh, wait a minute. We are not using weight and bias anywhere. I think we did a mistake. See, what layer norm does is times normalized shape times here, this is it. Just actually copy paste it and it will render it for us. Okay, times gamma and beta. So we do this times gamma, which is going to be the weight, plus beta. So we are going to say is out plus self dot bias dot no matmul self dot weight. Oh, perfect. Let's see if this works. Okay, the size of tensor 100 must match the size of beta and non-singleton dimension 0. First off, you know what, let's bring it down here. Yeah, what we're going to do is we're going to say print out. Okay, now what is out dot size? Oh man, so it's 100 cross 6 and the weight is times normalized shape. So out cross this thing plus this thing. Ah, perfect, it works now. Oh no, it's horrible. What if I used this? Uh, 2.6, 2.3, 2.7. Right. Behavior is the same. 0.67, 0.72, 0.78, 0.90. I mean, I don't know, man. One good thing is that we are not getting the lines are out very squiggly. Yeah, you know what? Let's just port it to our code. We'll see what happens. Normalize shape and EPS. This is going to give us EPS is equal to 1e minus 5. That was self EPS. Alright. Perfecto. 0.03, 0.43, 0.009. You know what? Let's just copy paste it to our main code, which is value head, policy head. For all these methods, I'm still using the base HFGPT because we have parameters for that. So for all the MCTS kind of part of work, we are using this model, but eventually we would like to use this model. Okay. So now what we are going to do is, so you have the first attention block, then you have the second block, but the output of the second block actually is finally we don't have ReLU here. We should. Okay. You know what, let's not do this. What we're going to do is we're going to simply say not MLP2 is you have the first attention block which works perfectly. For the second block, do we need a residual connection? I don't think so. What we can just say is layer norm 3 is now actually denorm, and yeah, and then all we have to do is self dot ln2 this thing. Okay. I've been facing a lot of problem with vast.ai. I mean, I knew this kind of thing could happen where if someone is already using my machine, then I don't get any access to it. I mean, still stuck in scheduling for hours now. Someone is using this machine straight for so much time, so long. You know what, let it be. Yeah, I didn't tell you about the loss function. Yeah, so let's just go with the loss function. So what I've done right now is we were using a categorical cross entropy, and the categorical cross entropy is like this. You have loss is basically equal to y times the log of y times the log of policy of which was correct plus 1 minus y times log 1 minus p. So what this particular value is saying, that it needs to be close to what the actual distribution should have been, while what this particular maximize the log of achieving this thing. So yeah, it's complete actually like this, negative loss likelihood. So what this piece does is that you have to try to match to what is your what is given in the target distribution, while this piece says that you need to minimize the minimize what was out of distribution. Now instead, what all these different algorithms use is just simply the first part and not the second part. So you can see what it actually should have been is you take whatever was your target, whatever was the policy that was predicted by the network, times just the first part of this equation. So you can see, so this way what you're telling it is that you just need to maximize the likelihood of choosing it, but you don't need to minimize the chances of not choosing it. So that was one thing. And secondly, they have the weight regularization, which in a way can always be achieved by using weight decay, because this is the loss. And so if you do the first order differentiation, all you get is d theta. So dl by d theta gives you like yeah, so it just is it gives you the first order differentiation times the theta, and that is what weight decay does. Weight decay is basically that the update of the weight is multiplied by some value times the weight itself. So the weight decay is not same as L2 regularization, but it behaves the same. The output is basically the same. All right. So that was the update on the loss function. Yeah, so now what we do is we have a log softmax, and after log softmax is basically this piece. Listen, yeah, log softmax is this piece, and for the target what we do is we create a one hot policy vector, convert it to hot encodings, and minus this thing matmul whatever the targets, and mean not sum, because see at the end of the day all of this is defined in the computational graph. So even if you all you do is you calculate mean. It just gives you a much closer value for or easier value for you to understand, because what you're seeing is not the actual values at which the updated, it's not the same as updated differentiation. Yeah, wait, so whatever. However, so coming back to this, we have already added this piece. I don't know why I'm doing this. It should be value. So using this method, all you have to do is you take whatever is the mean square error, and secondly you plus of this piece, which is this thing, and you already have the weight decay in the code itself. Oh yeah. And now we have the denormalization layer. The policy head is going to be the same, but the value head is now updated. Okay, let's just push this thing. GST git add this, git commit add denormalization denorm layer to value head because it's regression, and we do a git push. Oh, it's already 1 hour 17 minutes. Clearly my machine is not starting yet, so what I'm going to do is I'm just going to show you the Webapp web interface, and then I think we'll be done with this particular stream. Is there something left I would like to discuss? I have given you the updates. I've given you the simple normalization, denormalization layer, trained some networks. Yeah, I think I'll just give you an update on the Webapp, and that would be it. Go to python 3 play.py. So now what it is going to do is, this thing runs a simple Flask server. It is going to return, it's going to create a particular game. It's going to load one player that's basically a sample player, and yeah, let's see. That's it. That's the player. That's everything you have. It's a pretty straightforward thing. The code is super simple. I've designed it a little bit so everything stays in the middle. Then all you have to do is you start playing. If I do this, takes this, does this, can do this. See, it does play a lot stupidly. That's the problem with this network. Yeah. Yeah, doesn't really matter. Check. Oh shit, man! I should have at the undo thing. Oh my god, I'm such a bad player. What will it be? Oh, I have a check. Smart. Yeah, so the promotion works. Finally, there was some bug where the promotion was not working correctly. So that is fixed. Does it still kill it? No, you should have killed it, man. Bitch is going to come and haunt you. Oh, nice. So he is learning a couple of things. I don't know. Run, boy! Run! Oh, not here. They still promote to a queen? When? How? Oh, so it should have updated it as the queen, and if you have the queen, now you checkmate it. Checkmate. Right. Result is win. I should add better logging. So if it is if if done response res, no, you should update if res is equal to win. So res is equal to you win. Make response this, else game is draw, because no person, you cannot take one move in chess and lose. It's not possible. Else game is draw. Alright, so that's it for today's stream. I mean, I showed you a lot, all the updates. I showed you all the updates, and I demoed you. We played with denormalisation. I'm going to wait for the machine to get ready. Probably just rent another machine and run the entire code. Another thing that I can possibly do is take that NPZ file and put it on S3 so anybody can use it. Okay, that's it. Bye bye.